Hello, this is Dr. Strickland. In this video, we will investigate the deprotonation of a terminal alkyne. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. So deprotonation of a terminal alkyne means that we're going to remove that hydrogen from the end carbon. And we can do this because a hydrogen bonded to a carbon that is sp hybridized is considered acidic. And it's considered acidic because it can be experimentally deprotonated using a very strong base. So I wanted to show you this. These are electrostatic potential diagrams, which just show you, the red tells you areas that are electron rich, and the blue areas tell you areas that are electron poor, and then the colors in between are somewhere in between there, right? The yellow is closer to red, green is closer to blue. So what we're most concerned with is the hydrogens that are very blue, because they can be donated very easily because they have a large partial positive, which is how they get to be blue. And so you can see the 3.2 here for the hydrogen fluoride, 15.7 for the hydrogens on the water molecule. An alkyne is 25, which is significantly more than water or hydrofluoric acid. But if you compare it with an alkene or an alkane, that's a whole lot more acidic than that. And so we find experimentally that there are some bases that you can use to just pop off that final hydrogen from either acetylene, which is what we've got here, systematic name is ethyne, or from other terminal alkynes. So let's take a look at how that works. So we're just going to draw these structures in here so we can see the comparisons here versus just do ethene, and we'll just pick one of the hydrogens as ethene. And ethane, I think I'll leave those tucked down, and then pull these out. We'll pick one of these. But pKa is 25 here. pKa is 44, so this is almost 10 to the 20th times less acidic. So it's much less likely to donate that hydrogen as a hydrogen cation. And with ethane, with the pKa of 60, it's just not happening. Not unless you have a super strong base. Okay, so let's look at why it is that we would need a super strong base like these two that I've put up here, sodium hydride or sodium amide. And just while we're here, every salt is a cation and an anion. So you can draw out the cation and the anion. And for sodium hydride, it would be those. And then for sodium amide, it would be these. And both of them are super strong bases, the hydride ion and the amide ion. And they come packaged in these sodium salts. All right. But if I didn't have to work with sodium amide or sodium hydride, I would want to, because they're much tougher to work with experimentally. And we are missing a pair of electrons here. And they're also more expensive. So if I could use hydroxide, say from sodium hydroxide, I would want to do that. So if I did this acid-base reaction, and we know that the pKa of this is 25. If this is the proton donor and this is the proton acceptor, what are the products? Well, from what we talked about way back in Chapter 2, the products will always be the conjugate base of the proton donor and then the conjugate acid of the proton acceptor. And if you have an anion, very likely you won't be able to look up its pKa in the table, but you can pretty well assume that if you've got an anion as your second reactant, that it is the reactant base. So this is the reactant acid, and this is the product acid. The reaction goes in reverse, from right to left. This is the thing that would be the proton donor. And now we need the pKa's of the two reactant acids. So the pKa here is 25. pKa of ammonia is 36. And so you know just qualitatively that it's the side with the weaker acid that's preferred. And so this would be the side of the equilibrium that predominates. And so you would make this. And because this pKa is 10 or more units higher, you can assume that this would go in 100% yield. And we'll come back and look at that in a minute. But if you did the same thing with the hydroxide, where this is the acid, this is the base, so the predicted products would be the same alkynide ion, and then the conjugate acid of your base over here, which would be water. You're missing a pair of electrons too. Then the reactant acid has the same pKa right there. And then the product acid has a pKa of 15.5. Okay, so in this case, the weaker acid is on the left-hand side. So you know that at equilibrium, these guys would predominate. And again, this is pretty close to a 10-unit difference. So this is pretty much 100% on this side. So hydroxide is much less expensive. It's much easier to work with because it's not nearly as reactive. You don't have the hazards that you would have with sodium amide, but it doesn't work. This one works and that one doesn't. So what if we wanted to calculate the equilibrium constant of these two reactions? Okay, so if you're going to do that, you're going to calculate that and then use it to assess, what kind of yields you might have. Then the first thing you have to calculate is the pKeq. And remember, we do this by taking the pKa of the reactant minus the pKa of the product acid. That's 25 minus 36, which is minus 9. And then the KEQ is going to be 10 to the minus pKa, which is 1 times 10 to the 9. Now, you know that if your KEQ is greater than 1, then certainly the products are preferred. And if it's much greater than 1, you've got essentially 100% yield. All right, so what about this one? pKeq, take the pKa of the reactant acid minus the product acid, 25 minus 15.5. I beg your pardon, I'm off screen. There we go. It gives us 9.5. The KEQ is going to be 10 to the minus pKa, 10 to the minus 9.5, which is 3 times 10 to the minus 9. So in this case, the KEQ is on the other side of 1 by a bunch. All right, let's put that back up there just for completeness. Okay, so we can do it qualitatively by seeing which side has the weaker acid, and we can do it quantitatively by calculating the KEQ value, the equilibrium constant value, and then comparing it to 1. Okay, all right, so come on down here. The reason that people make these alkynide ions is because they're really good nucleophiles. And if you pair it with an alkyl halide as the electrophile, you can turn a terminal alkyne into a bigger internal alkyne. And so usually that's what we're going to do. So sodium amide is probably the best. That would be my go-to base. And so if we did an example, we could do something like let's just do this one. This would deprotonate this terminal alkyne, turn into that. And then if I had, like, say, bromomethane, which I'm going to draw like that, because I want to show you the electron movement. And this is the nucleophilic atom on the nucleophile attacking the electrophilic atom on the electrophile. Bromine's more electronegative than carbon. Carbon has a partial positive. We're going to break that bond, and we're going to end up with taking our propyne and turning into 2-butene. And then we'd have Br minus. Okay. All right, so this is a roadmap problem. What I want you to do with this is to supply the reagents required for each step. In a roadmap like this, I can ask you to supply the reactants, or I could give you the reactants and ask you to supply the products along the way. So one of the things I wanted to show you, as we look at this first step, we'll take an ethyne here and turn it into 1-butene. One. Keep our focus on those 2 sp hybridized carbons. One thing that you very often see is that if you can do 2 steps in a row like this, you can also list them like this. So in this case, this piece would have come from the alkyl halide. So let's say I use bromoethane. Okay, so basically what we've done is just stack them like that. But you have to make sure that you have the numbers so that it's clear that it's one reaction between the alkyne and the base. And then when that's over, then you've made your alkynide ion and you can add the alkyl halide as the electrophile. All right, so we added a piece to this right-hand sp hybridized carbon. And then if we check this next product, okay, so this is the piece that we added before, and now we're going to add a piece to the left-hand carbon. Well, I think we can do it exactly the same way. Still the super strong base, and since it's a 2-carbon piece, still bromoethane, although, you could certainly add, an alkyl piece of any length. And primary alkyl halides work better than secondary or tertiaries for reasons that we'll talk about in Chapter 9. All right, so if we want to take our alkyne here and turn it into a cis-alkene, what do we need? We're adding 2 hydrogens, right? So it's a reduction. But this is the one that involves Lindlar's catalyst. It's a cis addition, a cis product that was formed by the syn addition of hydrogen gas across the alkyne. And then finally, if I wanted to take this guy and turn it into this alcohol, I'm still tracking these 2 carbons. I'm adding water across those 2 carbons, because you can see this carbon has 1 hydrogen in that ethyl piece, and now it has 2 hydrogens in the ethyl piece. So what could we use? Well, I think since it's an internal alkyne, I think I just use water and sulfuric acid, because this is a symmetrical alkene. And so, it doesn't matter if we form the cation here or there, we're going to make the same product either way. And because it goes through a carbocation intermediate, we're going to make both the R and the S and H. All right, so that is the basic story on removing a proton from a terminal alkyne and why you might want to do that. All right, so if you have questions, please send them to me.